The overall goal of this protocol is to generate and coherently control pulsed quantum frequency combs, which may be used for quantum information processing.
This method can help us provide the tools for fundamental investigations of quantum mechanics and for realizing non-classical technologies, such as quantum communications and information processing.
The main advantage of this technique is that well-established telecommunications components and protocols are used to generate and control complex optical quantum states in a reconfigurable and scalable way.
We had this idea when we talked with my colleague José Azaña, who is an expert in telecommunication processing, and we realized that we could transfer his tools to the world of quantum optics.
Set up the components of the system on an optical table. The system has stages for generation, control, and processing. This depiction provides an overview. All elements are connected with polarization-maintaining optical fiber. For now, focus on the generation stage. This stage features an on-chip micro-ring resonator embedded in a larger external cavity. The external cavity is made of an electro-optic amplitude modulator driven by a signal generator, an isolator, and an erbium-doped fiber amplifier providing optical gain. There is a narrow filter with a pass band selecting a single microcavity resonance, and a notch filter routing the generated photons to the control section. With the cavity disconnected, initiate the erbium-doped fiber amplifier. Use an optical power meter after the amplitude modulator to measure the transmitted power. At the modulator, use a power supply to apply a DC offset to have the transmitted power.